All right, so we are going to continue understanding the physics of the guitar string, and we've already done damping, but now we're going to add stiffness. And what we're beginning to see is that a guitar string, what we should be seeing is that a guitar string is close to being ideal, right? Meaning the features of being, well, the bugs of being damping, of being subject to damping and subject to stiffness, don't change the physics very much from the ideal. And the ideal is always referred to the ideal wave equation. So our guitar strings we're discovering are actually we're going to be discovering, and we've already discovered a little bit, are well modeled by this ideal wave equation. And the key that makes this so important, or the point that the ideal wave equation tells us, is that the frequency of every harmonic, right, the nth harmonic frequency, is some multiple of a fundamental frequency. And that fundamental frequency is the speed of sound on the string divided by twice the length of the string, which we know is now, which we can understand to be related to the square root of the tension divided by the mass density times C over, oops, that is C, right? It's divided by 1 over 2L. And this N here is the harmonic we're interested in. So for the fundamental mode, it's N equals 1. And for all the other modes, it's the second harmonic, N equals 2, and et cetera, et cetera. And so that is what the ideal string is all about. Now, what we learned was that if there's damping involved, right, if we have damping involved in the last analysis, we ended up adding a term which we expressed this way, minus 2k du dx. And this term led to an overall factor for the dynamics of each mode to be e to the minus kt, right? This factor here. And that damped all the modes because as time, right, this is time right here. This t is time. This k is our damping factor, which has to do with how long it takes the mode to damp away. And this acted on every mode, and it tended to drag the mode down to 0 as time went on. The amplitude of the mode would go to 0. And what we kind of discovered was, you know, K for a guitar, it's fair to say it's about 1/6 or 1 over 6, where 6 is in seconds. So it's 1/6 of a hertz, I guess, is a unit that we could consider K. T, of course, is time, and time is in seconds, right? So when T equals 6 seconds, then KT equals 1, and then you have e to the minus 1, which is something like 0.37. So we know that all the modes drop down to about 37% of their original value after 6 seconds, right? That's what this K is, the K in this equation. And so by just measuring how fast your guitar strings drop in, or how fast the signal drops from the guitar string, you can figure this out. Now you have to be a little careful because when you use a spectrum analyzer to do this, right, the spectrum analyzer will tell you like the one mode is this loud and another mode is this loud, and it looks kind of like that. If you just watch how long it takes this to drop to 37% of its original value, that would probably be wrong because this measures the power, right? This is the power. And this here is referring to a factor that suppresses the amplitude, right? And the power is related to the amplitude squared. So you've got to be a little bit careful. In the end, you're looking for something around an 8 decibel drop for what it's worth. We'll talk about that in later lessons. But the point is by using a spectrum analyzer, you can measure this value K. The point being, though, that 1/6 of a second is actually relatively large because what we also figured out was that the frequency of the damped spectrum is equal to the frequency of the undamped spectrum times a certain factor. And this factor is in the square root depends on the damping, the length of the string, the speed of sound on the spring. Remember, whenever you see C, you think the square root of the tension divided by the mass density, right? That's what C is. And it depends on the harmonic number in pi. So since the harmonic number is in the denominator of this term, first of all, if K is 0, this term is 0, and the spectrum of the string, of the damped string, is the same as the spectrum of the undamped string. Of course, if K is 0, the string is in fact undamped. Now, as the speed of sound in the string gets greater, which is another way of saying that the tension on the string is greater and greater, or the mass density is smaller and smaller, this piece goes towards 0. And again, the undamped, or the damped frequencies and the undamped frequencies are the same. Likewise, as you get to higher harmonics, this term gets smaller and smaller. So the effect of the damping on the higher harmonics becomes less and less. Now, today we're going to study stiffness, and we're going to see the opposite. The opposite. The higher the harmonic, the more the inharmonicity. But this can be considered the inharmonicity factor. And the point is that when K is when K is around 1/6, and L is 0.6477 meters, which is the scale length of the guitar we're studying. And with any reasonable measurement for the tension over the mass density of a guitar string, this number is very small for a guitar, which basically means the inharmonicity in a guitar, because of damping, is really, really negligible. Now, when I say it's really negligible, it's really small, that's not a very scientific analysis, right? I'm just saying, oh, it's too tiny. You can measure exactly this difference, and we're going to measure that difference eventually in cents, right? In cents. But we haven't discussed that here yet. So talking about the difference between this and this in frequency units of cents is something we're going to do a little bit later. But the fact that this goes to 0 very quickly and is small relative to 1 for almost all reasonable values of K tells us that the inharmonicity due to damping is very small. So now we turn our attention to stiffness. What is stiffness, and how does it affect the guitar string? Well, now the ideal guitar string, right, we're drawing as a straight line, right, because we didn't give it any thickness or any dimensionality except length, scale length. But what's a real guitar string look like? I mean, you can definitely imagine this with a bass string or piano string, but a real guitar string actually has some thickness, right? And here's just some exaggerated thickness so we could see it. The problem is that when a guitar string bends, right? When a guitar string bends, in this region, right, you can see that this part of the string is actually compressed, and this part of the string, the part above it, is actually stretched, right? So there's a stretching and a compression, and these give rise to internal forces, or inside the guitar string. And those internal forces have a significant effect on the guitar string's vibration, or the string's vibration. I'm going to still call this a string in the sense that its length is much greater than its diameter, right? So its length is much greater than its diameter. But it's not a true string. A true string would be like this, where it would have no internal stresses, right? A true ideal string has no internal stresses. So this is sort of a non-ideal string, I guess is what we want to call it. Non-ideal string. And piano strings and bass strings and guitar strings are all non-ideal. The question now is, if we take into account these internal forces, how does that affect the frequency spectrum of the overtones of the string? All right, that's the question we're here to answer. We're basically going to derive yet another version of the wave equation and solve it to get that answer. Now, the reason you know that this applies at some level to guitar strings is that when you buy a guitar string, it comes wrapped in a bag, right? And it's all wound up in a circle. And then I guess the the ball is at the end, right? But if you untwist it, because usually it's twisted in a way where it maintains its circle shape, but if you untwist it, it immediately tends to straighten out, right? And it becomes a nice straight string sitting there. The fact that it unwinds itself is a result of these internal forces inside the actual string. Inside the string, these internal forces, these areas here where it has been, where there's compression, right, where the string is compressed, the forces tend to push it and want to straighten it out. And the places where it's stretched, the forces want to pull it and squeeze it together. And this force pushing this way and that force pushing that way tends to create a moment of force that will straighten out the string. And that's a real effect, since your string doesn't just sit there and flop on on your workbench when you're changing strings and you have to literally straighten it out yourself. Clearly these forces exist, and those forces affect the vibration. So now we know that the vibration of the stiff string will be some, there'll be some, the unstiffs, the natural frequency of vibration for the ideal string times the harmonic number. That would be the normal, perfect ideal string. But then there's going to be a factor multiplying this. That's going to be the inharmonicity, right? The inharmonicity factor, we'll call it. And that inharmonicity factor is for stiffness and damping, right? We already know what it is for damping. It's 1 minus KL over N pi C, right, squared, right? So we know what it is for just damping, but now we are going to do it for stiffness and damping. So that's our goal, and it's all through the solution of a new form of the wave equation. So first thing we got to do is we got to get an understanding of these internal forces and how to handle them. So let's begin with that. So here is a piece of our non-ideal string, right? And it's got some overall length, and it's bent. And in order to be bent, there's definitely some moments being applied to this string that maintain its bent shape, right? But we're going to use sort of the same general idea to track our solution. We're interested in the displacement of the string, U over its length x for time, right? So this string has a displacement from its equilibrium position that we call U. And the wave equation, of course, is a differential equation, a partial differential equation for our formula for U. So now let's look at just a little piece of the string. Let's just look at, say, this piece right here. And actually, you know what? I should draw it, and I should flip it all around. Hold on, let me flip this around. Here, I want to do it this way. And then I'm just going to look at one little piece of the string, say right there, and I'm going to redraw that segment. Now, as we said before, part of this string is being compressed because of its bending, and the other part is being stretched. Each of these cross sections is considered perpendicular to a certain line, though, and there is a line that is neither stretched nor compressed, right? It is just as long as it was before the bending. And the reason this is possible is because these endpoints are actually allowed to move. This here is supposed to be these cross sections. Maybe I should make this cross section a little bit. Actually, in both cases, I should make the cross section look a little bit more purely perpendicular to this neutral line, right? The neutral line is the line that has no bending at all. So to be perpendicular would have to look more like that. But the point is this part, the top part is in compression, the bottom part is in tension, right? And the overall situation is that we have some physical properties in the material that we can use to sort of take this all apart. Now let me put some, the notion of the curvature here, right? This distance, this neutral line, right? I'll call this neutral. this neutral line is got a curvature of, and I think I'll use rho. Rho is a typical symbol for curvature. That neutral line is a curvature rho, and we are going to consider another line that is not the neutral line. I'll put it in red here. And that's this particular fiber of the string, right? The string has a little fiber here. And that line will be, that fiber is going to be a distance z above the neutral line, right? So we're making this sort of mathematical model of the internal structure of a string. So the question we want to answer first is, what is the length? What is the length of this particular fiber, this little fiber I just drew, right? The length of this fiber relative to the length of the neutral fiber, right? The uncompressed and the unstretched, fiber. What is the length of this versus that? And that's not very difficult to determine because we have got this rho curvature here. So the length of the neutral fiber is, we have to have some amount of angle, I guess, of our little, we're having this is a small segment of string, right? This is a small piece of string, just like we did the first time we did the wave equation. We analyzed something that was very tiny. So this small piece just subtends an angle d theta, and so that the neutral length has a length of rho d theta. And the compressed part at z, right, that has a length, let's say L at z, of rho minus z, right? That's this distance. Rho minus z is just the distance up to that part, but it's still times d theta. And so what we're interested in is the strain. These are now engineering terms, right? This is interesting. This is a little less, the language is still physics, but it's physics with such a heavy degree of application that this whole process really feels more like engineering. Although, truth be told, the engineers just use the final formulas, where the physicists, we're given the burden of deriving them. But we're interested in what is the strain here. And the strain is defined as the difference in length divided by the original length when it's under compression or tension. Now, in this case, it's under compression. But the delta L, let's see, what will delta L be? Delta L will be, so this will end up being L at the point Z minus L over L. That's strain. Strain has no dimensions, right? It's length over length. It's the change in length given the amount of length, right? And that's what strain is. So this isn't a 2, that's a Z. Better fix that so it doesn't confuse me later. LZ. So LZ minus L, well, this is pretty easy, right? It's just going to be rho minus Z d theta minus rho d theta all over rho d theta, right? The d thetas cancels out, the rho cancels with the rho, and you get the strain equals minus z over rho, right? That is the strain. And the strain is usually given by the Greek letter epsilon. So this is the strain at the distance z above the neutral line of our little string element. Well, that's excellent, because once we know the strain of our things, we know the stress, because this piece of string is actually a metal wire, right? It's a metal wire, and it has a value that's typically given by the letter E called the Young's modulus. And the Young's modulus tells us that given a certain amount of stress on the wire, right, and stress equals force per unit area, right, force per area, then we will accomplish a certain amount of strain, right? So the stress on the wire, which is related directly to the forces in the wire, is equal to the Young's modulus of the wire times the strain of the wire. And now we have something to talk about the forces that are inside this little segment of wire. And the way we'll do that is we'll say the force per unit, per bit of area, right? Stress is really the differential of the force with the differential of the area, right? And that equals E epsilon. So the formula we get is that the differential of the force equals E times the strain times the differential of the area. And for us, this equals minus Z over rho, right? That's what the strain is, times E dA. So that's what the differential amount of force is. So the little amount of force that's, the differential amount of force at this location is given by this expression right here. And to interpret that, understand that this is a cross-section. We're looking at a piece of the length of the string, but if we turned it on its side, let me see if I can erase this real quick, like these words. If we turned it on its edge and we looked at it, we would see a circular cross-section, right? And it would still be the case that, you know, we have this, there is still a neutral area. I draw the neutral line in the middle, but that's not necessarily the case, right? The idea is that the whole force, the entire force on this wire would be you would have to integrate dF, right? You would have to get integrating this formula here, which would now be equivalent to integrating minus Z over rho E dA. So you end up integrating over the area, right, to get the total force. So that's a start. We've got this formula for this differential force. Now we want the formula for the differential moment, right? The differential moment. But that's not really too tough because the differential moment is going to be the differential force, and we're going to take the moment around this line, this neutral line. So it's this force times the moment arm, which is Z. And in the compressive side, the force is always going in the compressive direction. And in the tensile side, the force is always going in this other direction. But the way the cross products works is they contribute to the same moment, right? Because if you apply the right-hand rule to all the forces on this side, you're going to get a moment that comes out of the board. And likewise, if you do the same thing to little guys to the force elements on this side, on the compressive side of the neutral line, they are also going to come out of the board. So all you have to do is integrate this expression over the area, right? Basically integrating Z over the area. So you can ignore this sign to get our moment, as long as you remember which direction the moment's going in. And so this moment is actually going to end up being, well, the differential of the moment, right, is going to be this differential of force. I guess the way I have it written here, it would be Z dF, right? Understanding that these are vector quantities, dm and df. And that ends up being Z multiplied by the Young's modulus times the strain, which should equal the Young's modulus. The strain is Z over rho dA, and then this Z here makes that a Z squared. And that is the differential of the moment. So the differential of the moment equals E Z squared over rho dA. And so the total moment is just the integral of the differential moment over everywhere where the differential moment is non-zero, which is everywhere where the area is non-zero. So E is a constant, and rho is a constant. So we get the integral of Z squared dA. And this integral is always called the moment of inertia. So that ends up being EI, the moment of inertia, over rho. EI over rho. And that equals the moment. Now, once we have the moment, now we have to think about this rho, right? So we're working for a differential equation that is designed for, we're trying to solve for u of x and t. That's our formula for the shape of the string. So it turns out for any function, right, this is all from basic calculus, right? Well, this is all from calculus, but for a function, the curvature of the function is related to its second derivative. So u, in this case, its second partial derivative with respect to x. And the radius of curvature rho is related to this number in a way that can be calculated from elementary calculus. The basic expression goes like this. 1 over the curvature is the second derivative of the function. I guess in this case I should write u, right? Because we're talking about u. I just pulled this off of a let's see, so it'd be u, and I should use, so ux, and then this should be uxx, right? So this is the expression for 1 over the curvature of an arbitrary function u, right? This second derivative with respect to x divided by this factor of the first derivative with respect to x. So the point is that if the first derivative with respect to x is very, very small, then the denominator is 1, and then this becomes uxx, right? And that is an assumption we make, right? We're going to be making the same assumption we always make, which is that the slope of our guitar string, see here, that's really steep, right? We don't have that. Our guitar string slopes are always very, very, very small, which means this denominator is small, which means we can say 1 over rho is approximately equal to the second derivative of uxx. So what does this mean for our moment equation? Well, our moment equation is EI over rho equals the moment, right? So if I write down the moment equals EI over rho, that now equals EI over our function second derivative, its second partial derivative with respect to x. And that is actually a really, really important expression that takes our internal forces and tells us something about our internal forces given the shape of our final formula, right? Given our final formula, we can learn about the internal moments through this expression. And this here, the cross-section, you know, the dA, the cross-section is built into that. The material properties, of course, comes in through the Young's modulus, and the physics comes in through the moment. And then this is the geometry of the string. So we have the geometry. I guess all of this is the geometry of the length. This is the geometry of the cross-section. This is the physics of the material engineering properties, and these are the internal forces. And there is a sign here, right? Depending on how you orient your coordinate system, this moment might be positive or negative, so you have to sort of keep track of that. But that's not really going to be very important for us. Now, another important thing we have to understand is another way of looking at the moment, right, is if we have our rod, beam, stiff wire, is that we have these things called shear forces, right? We have to understand the difference between a shear force and an axial force, right? The axial force is the tension in the wire. This is the tension of the guitar string. Shear forces are applied perpendicular to the wire. So if I take any little piece of the wire out, shear forces are applied on the sides, right? And the moment, the bending moment of the wire at any point along the wire, there's a bending moment. And that bending moment is a result of the integral of all the shear forces, which sometimes are called Q, the shear forces around during the length of the wire. So if I integrate these shear forces down the length of the wire up to a point, then that integral will be the bending moment at this particular point in the wire. Right? So the bending moment is related to the shear force. The thing we need to remember is that the shear force is the derivative of the moment with respect to this direction along the wire, which we're calling x, right? So the shear force at any point is related to this derivative. And using our new expression, right? Using our new expression, we now can say that the shear force equals EI times the second derivative, but it's this, it is the, I guess we have to go with partial derivatives here, partial x, right? It is, which will end up, if E is constant and if I is constant, this is going to be related to EI times the third derivative of our formula, right? So now we've for shear forces, we are connecting those to a third derivative. Okay, so now we look at our little piece of beam, and what do we understand? Well, we understand that our little piece of, I keep saying beam because the analysis is for a beam, and we're basically trying to figure out is how similar is our guitar string to a beam, right? So we take this little piece, and the little piece is just a little piece of this long string, right? So we just take out this little part. Right here is the part I want to take out. In fact, let's go to a new screen and do it. So here's our little piece, right? This little piece has a dimension, a very small extent, which we call dx, just a little infinitesimal extent. And we know that on the left side, it is subject to a bending moment. And on the right side, it is subject to a bending moment, right? And here the bending moment is going to be the bending moment on the right side is going to be the bending moment on the left side times the partial derivative of the bending moment with respect to x times dx, right? The bending moment is a function along the wire, right? The beam itself, at every point, there's a moment, right? At every point, there's a moment. So the moment is a function of x, right? So we can take that derivative with respect to x and to see how the moment is changing along the wire. So the moment over here and the moment over here, right, are different by the derivative of the moment times this little amount of space of differential element size, right? And the same is true for the shear, right? The shear here is some force, we call it V, that's perpendicular to, I guess I was calling it Q, right? Q, and then here the force is going to be Q plus the first derivative of Q with respect to X dx, just like before. But now we have formulas for Q and M, right? We know what Q and M are, right? So I can write, so with this expression, we're after, for example, after this guy, we know how dq dx works, right? That's the partial derivative with respect to x of the moment, which we calculated as this expression. Now there is a question about a plus or minus sign here, right? The way we have these moments oriented. Because I didn't lay down a coordinate system, I guess I do have dx here. So x seems to be positive in this direction. So this moment here, for example, at Q, right, which is perturbed by this much, that moment would be negative, meaning that would be going into the board. So a minus sign here would make a lot of sense. So this is our expression for dq dx. But we also know that the expression for just straight up Newton's laws tells us something too, right? So we know this from our analysis of the physics or the mechanics of the wire, but we also can just apply Newton's law straight up, right? And what we notice is that this is a small segment of string, right? So what is its acceleration? What is the acceleration of this little piece of string, of our guitar string? Well, we need to find the unbalanced forces, right? The unbalanced moments will tend to spin it and rotate it, but the unbalanced forces will tend to accelerate it up and down. So its displacement is W. So we're interested in its acceleration, which is W tt, right? It's second derivative with respect to time. Well, what's the unbalanced force? Well, Q going up is balanced by Q over here going down, but then you have this plus delta. So this piece here is the unbalanced force. So force equals mass times acceleration, right? So that equals mass times WTT, because we're still assuming that all the acceleration is up and down, right? That's another transverse vibrations only, right? Transverse modes, right? There's no longitudinal movement like that. That doesn't exist. That doesn't exist. So what is the mass? Well, the mass is the density of the string times the area of the string times the length of the string times WTT. So that is the unbalanced force, but it also, that unbalanced force is this piece here, dq dx. So it's that must equal partial q partial x dx, right? So the dx's cancel, and you get partial q partial x equals rho a, and then I went with w, but I meant u, right? This is u. We're always doing everything in terms of u. UTT, so it's partial u squared partial t squared, right? But this guy, we now know from here, is going to be minus ei partial to the fourth u partial x to the fourth equals rho times the cross section times partial squared u partial t squared, where I'm going back into this partial notation so it looks a little bit like the wave equation. And let's see how close I am to being done. Well, that really is almost it. I guess I just need to sort of clean it up a little bit. But this is a wave equation, right? This is a wave equation. You have partial u with respect to t squared, and then you have a fourth derivative of u on this side. So this is very far from the ideal wave equation in the sense that you've got a fourth derivative and a second derivative, fourth derivative with respect to space and a second derivative with respect to time. But that is the wave equation that tells us how to solve for u, which is our equation for the string. This is an equation that solves to give us a formula, right? And that formula is u. So you might think that this is the equation we want to work with. And I mean, it is an interesting equation to solve, but the problem is it is only valid for beams, right? We've only forces that we considered in this mess were, if you look, were shear forces and moments. We didn't have any of the tension forces that are important for guitar strings, in fact, that dominate guitar strings. So this isn't quite the equation we want, but it is very close and it is relevant. There was another issue too, I think. One was back here, where was it? Back here when we looked at this piece of string, we had this neutral line, right? But obviously this line, in order for it to be the same length as it would have been without bending, you have to allow these endpoints to move a little bit left and right. And this is effectively longitudinal motion that we consider to be small. That all kind of gets washed away because this angle, this little infinitesimal bit, is infinitesimal. So that motion becomes infinitesimal. So there are a few things there, but the bottom line is this equation is good for a beam, and we need to consider it for a string that has the tension motions. Well, the first thing we want to have a look at is we know what the wave equation was, the ideal wave equation, right? It's here in magenta. And they both share this t squared, this second derivative with respect to time. So let's take the beam equation and just solve it just for the second derivative with respect to time. And if we did that, we would end up with, let's see, minus EI over rho A partial 4U partial X4, right? This is for the beam. These are two separate equations. I don't want you to think that we're going to immediately set this equal to this, right? That's not what we're going to do. But this is the beam equation isolated for the second derivative of our formula with respect to time. And this is the ideal wave equation. So what we're basically going to now say is that these two effects happen together, right? They're isolated effects. If you did the analysis that would derive the wave equation and the analysis with the beam equation, you discover that there'd be no, with the assumptions that we have made, right, there would really be no interference. They wouldn't be any different. You could do them together. So when we went back here, when we did this analysis, if we had included these tension forces, which we didn't include, and we had, oriented this at an angle, so not only is it just bending, but it's also at an angle, we would have ended up with this expression in our result. And therefore, we're just going to add it in there. So the equation that we're going to look at initially, part of the wave there is going to be this equation. And this equation includes the regular tension forces and these internal stresses and strains shown, reflected by the Young's modulus. Now, on top of that, so there are people out there who've solved this equation, and you can find solutions to this in the literature. You can definitely find solutions to this in the literature for the beam equation. And then when you look a little harder, you can find solutions to this in the literature, because there are people who've studied the musical instrument strings, and they understand that there's this inharmonicity due to these internal stresses, and that it needs to be accounted for. And so they've examined this equation. But what nobody does is they don't include I shouldn't say nobody that I saw included the damping part as well, right? So the damping part is also independent of all of this, and we're just going to throw it in there. So we're going to solve the full equation that includes the internal stiffness and the damping as well, right? We're going to do all of this together. And we're going to see that the bulk of the string is modeled well by this equation, which we've already done. And this part, the part that reflects the damping and the stiffness, has an effect as long as the stiffness is large and the damping is large enough to show shifts in the frequency. So this part is going to give rise to all of our inharmonicity, right? All of the inharmonicity is going to come from these two pieces. By definition, by the way. This is just a definition. This part is this ideal piece. Because it doesn't have these complications, it's simple. And because it's simple and obvious and approximate, we call it the harmonic. This yields the harmonics, right? And anything that diverges from that, we call inharmonic, right? It's not like it's less physically meaningful or relevant or anything. The inharmonicity always will exist. Whether it's noticeable or not is another question, and we'll do that study in another lesson. Okay, so now let us solve for the this wave equation, which because it's not typically solved in the literature, and in honor of the passing of guitar legend Eddie Van Halen, we're going to call this the Van Halen equation, right? The Van Halen equation. Why not, right? Okay, so let's begin. We begin by writing it down in this sort of neater form where we don't have to carry around all those symbols for partial derivatives, but this represents the second partial derivative of u, the displacement, the transverse displacement with respect to time, the second partial derivative of u with respect to distance from the nut, which is the x-coordinate, and this is the fourth derivative of u with respect to the displacement from the nut. And 2k is our damping coefficient. Alpha squared is going to be all of the factors that all those numbers that go into the stiffness, which was I over, I think, rho times the area, things like that. We'll go back on those units. We'll figure out those units again later. And let's, well, actually, you know what? We should nail those things down now. This is the equation we're going to solve. We better understand it, right? Of course. So C, we know, is the square root of the tension over the mass density. We know that K represents the time to about 1 over E equals approximately 30.37 amplitude decay, right? Right? So that's a very simple model for decay. And alpha is going to be, well, alpha squared, right, is going to be, alpha squared is EI over the density of the material that makes up the string times the cross-section of the string. So we're going to break that down, right? So if we have, and we're just going to look at it in a different way. We're going to look at it as more guitarish, which is, so density is mass per length cubed, and area is length squared. So obviously rho A is going to be mass per length, which of course is the linear mass density mu, which is what we typically cite for a guitar string, right? So alpha squared equals EI over mu, and of course alpha equals the square root of these things, all right? So with all that in mind, the next step is pretty straightforward, right? The next step is just separation of variables, as always. It turns out that this equation can be solved by separation of variables just like the others. So we assume that u is a function, is separable into the product of a function of just x and a function of just t. And when we do that, we end up with, we substitute that into our original differential equation, and we get this large equation, which we now proceed to separate, and we use a separation constant of minus lambda squared. I'm not going to explain why, because if you look in the other lessons, right, for the other equations, it's all the same thing. It turns out that you're going to have trigonometric functions and second derivatives, and it's just more convenient to have a minus lambda squared as your separation constant. And we've sort of learned enough about it now that we can do it. So this becomes t over t plus 2k t over t, right? Now, I'm keeping the c squared. Notice in this version, I'm keeping the c squared on the spatial term. In, I think, the original solution of the wave equation, we kept the c squared, we kept 1 over c squared with the t. So this would have had a 1 over c squared in it, but we're just keeping it with the x this time, and it really doesn't matter. Its effect is to change the units of lambda, right? That's the ultimate effect of that choice. But the choice itself is not that important. And then this becomes x over x minus alpha squared x over x equals minus lambda squared. So these are our two ordinary differential equations, right, that we have to now solve. And what's interesting is we have solved both, we've solved this one before, right, effectively. And so we're just going to write down the solution to this one. This one we're going to have to work on. So this first one will become, let's see, I'll do it in blue here so I know it's the separate one. It's going to be t plus 2k t plus lambda squared equals 0, right? That's the, this is the ODE, I wrote ODE over there, but this is the one that's more familiar, right? This is just your straight second order ODE, right? Basic. You can literally look at that and write down the answer. And this other guy, what is it going to be? It's going to end up being x minus C. See, I think I got to go C squared over alpha squared, right? And then, I think, let's see, that'll come out minus lambda squared over C squared. Oops, I forgot my XX, right? X minus lambda squared over C squared equals 0. Is that right? Yeah, because alpha divides a negative, so this becomes positive, this becomes negative, that came over as positive, but divided by minus C squared, not C squared, alpha squared, right? Alpha squared. All right, so there we go. So this is our second ODE. We haven't solved this one. It's a fourth order ODE, right? Fourth order ordinary differential equation. But it is ordinary, it is fourth order, it is linear, so there's nothing about this that is in principle hard. And in fact, it turns out to be quite easy. Okay, so now we have our mission. We have to solve these two ODEs. This one we've already solved, right? The version we solved previously had a C squared in it as well, but we kept the C squared on this one, so we don't have that anymore. So I'm going to write down the solution with that in mind. So let's first look at, well, let's see. Let's first look at, which solution should we look at first? Let's first look at the solution for this guy since it's harder. So this is the equation. We're going to, just because there's a lot of algebra here, we're going to simplify it by adjusting these constants a little bit. And I'm going to simplify it to the fourth derivative of x, but then c squared over alpha squared, I'm going to call 2 beta squared, because there's a characteristic equation here with a quadratic equation solution, and if we have it as 2 beta squared, beta is going to come out and be pretty easy to handle. And then this we'll call just delta squared x equals 0, right? And obviously beta is going to be defined as c over the square root of 2 alpha, right? So beta squared equals c squared over alpha squared, 1/2 of that, and then that's where this factor of 2 comes in, right? This factor of 2 right here. Okay, so attacking this is done with just, we have to write down the characteristic equation. The characteristic equation is r to the 4th minus 2 beta squared r squared minus delta squared equals 0. And the solutions to that characteristic equation are the r squared, because now this is a quadratic equation in r squared, right? So we use the quadratic equation to solve this. No problem. And so we get r squared equals 2 beta squared over 2 plus or minus the square root of, I think it's 1/2 times 4 beta to the 4th minus 4 delta squared. Now you can see why we chose all of these things. This equals beta squared plus or minus, these 4's come out, cancel with the 2, and you get square root of beta to the 4th minus delta squared. Is that right? Now with this, and looking at beta equals c over 2 alpha, understanding that c is the square root of t over mu, understanding that alpha is ei over mu square root, I think, right? And understanding those things, you can now make a complete substitution back into here, and you end up with r squared equals this expression here, right? So you've got the tension on the wire, right? You've got the modulus of elasticity, that engineering feature of the wire. You've got the mass density of the wire, right? So all that's sort of the engineering and material science of the wire. The tension shows up over here. This tells us that the square root only applies to here. So I've got that little line on my square root, so that we know this is definitely outside the square root. And lambda is our separation constant, right? Lambda is the separation constant, so that's what connects the two equations. And then, of course, you have the plus or minus. So there's two solutions for r squared, right? So there's sort of r squared 1 and r squared 2. But I guess the way to write that is we don't want to confuse these subscripts and superscripts. So we have to write r1 comma 2 squared equals this, right? So now we're getting there, right? We haven't fully solved this equation yet because we've only found two solutions and we know there's four, but that's pretty easy because this in itself is an equation that all we have to do is take its square root. So what do we end up with when we do that? Well, we'll start with we'll take the root of the positive solutions, right? So R1, we're basically going to look at R1 squared. So I guess I have to give a new name for, there's going to be four of these things. So R1 ultimately, I guess I need to change the name of this to RAB, right? And R1 equals the positive square root of RA, and RA is the positive square root here, right? So, all right, so anyway, it's going to be the square root. That equals the first of the four roots. That's R1. R2 is going to equal minus the square root. Oops. Let me do it legibly. Minus the square root of RA, right? So it's going to equal minus the square root of the same thing. There, I copied it, and I'm going to put a little minus sign there. Now notice that we're in good shape here. T squared will always be positive. E is positive, I positive, lambda squared positive. All these numbers are positive. So this is always going to be a positive number here. So this negative sign matters, right? Because this whole thing is positive. So that's two of the four roots. That was dealing with this sign here, right? So we dealt with this plus sign already. So now to deal with the minus sign, right? What would happen there? Well, I guess we better do it separately. I was about to just sort of change things around, but we're going to need these roots later. So there's R1 and R2. Let's see now. R3 is going to equal the positive, let's see, it's going to equal this guy, but inside here we've taken the negative, right? And R4 is going to be the negative version of that, right? So it's going to be this guy here. We take the negative root, but then we take the second negative root. So that's all four roots. Now looking at R3 and R4 is important because what we want to do is we want to get rid of that minus sign. So what we're going to do is because remember this guy here is always positive, so this guy now is always negative. And so there is, and also, if you notice, this expression here is always large. This square root here is always larger than t, because this is positive, this is always positive, so that sum is going to be larger than t squared. The square root is going to be larger than t, because these functions are monotonically increasing, that kind of thing. And therefore, this will be a negative number that's larger than t, which means everything under the square root will be negative, and it'll be an imaginary. So pure imaginary. So R3 and likewise R4 are both going to be pure imaginary. So let's anticipate that by pulling out a -1 under the root and then just pulling it out front as an I, right? So we pull out a -1 under the root and we end up with an I like that. So we now know that R3 and R4 are pure imaginary and R1 and R2 are pure real. So we have 4 roots, 2 imaginary, 2 real, and the imaginary roots, of course, are just like we expect. They're complex conjugate pair, right? So we have now found the 4 roots of the characteristic equation for our spatial differential equation. And I've replaced all the physical parameter constants in here. I just use these numbers to help us solve the quadratic equation, and I immediately plugged in the final numbers. I don't know why. I guess I could have kept the betas all the way through, but I decided not to. Okay, so there's our 4 roots. Now what do we do with the 4 roots? Well, we go back to our elementary theory of linear higher order differential equations, and we realize, hey, the answer is going to be this. Each root is going to be part of the exponent. Oops, I forgot my t's, or I forgot my x's. Right, all these x's belong up there. And the coefficient of those x's are just going to be each of these roots. But for the very same reasons as occurred in our last lesson, we choose to write this using the trigonometric forms, right? So we're going to write this as a hyperbolic cosine R1x, because remember, R1x was the real one, right? So it gets put in the hyperbolic. B hyperbolic sine R2x, but R2 is just minus R1. Yeah, so it's really just R1 again, right? R1x, right? Because R1 and R2 differ by just the sign, and what we're really doing is we're using that fact that R2 equals minus R1 here, right? We erase that, and then this becomes minus R1, and that allows us to combine these two into a hyperbolic sign, with the caveat that we're actually splitting them both up so that we can combine them together in this form, right? There's always a way of doing that. A and B are not the same, by the way, right? This is, I guess to be technically correct, I should write this as A hat and B hat, right? But then we do the same thing for the imaginary parts, right? R3 and R4 are imaginary, so we know we can make them sine and cosine. So I'll write C hat sine, or I guess, yeah, C hat sine R3x plus D hat cosine R3x, right? And this is our solution for the spatial part of our answer, of our wave function. And R1 and R3 are given by this expression right here, which is a very complicated piece of physics, and this expression right here. The real parts of these two things, right, of this and this, this whole thing is real, and it's got a plus t. This is the imaginary part, but its coefficient is the same as R1, but it's got that minus t there, and of course the I, right? And in fact, what I should be doing, right, is R3 is defined with an I here, right? That's a bit awkward because I just want the coefficient here, right? So when I write R3 here, I'm really writing the old definition R3, but over I. I got to get rid of the I. That's sort of built into the definition of sine and cosine. Because if I substituted literally, right? If I substituted literally cosine I times the square root of something, then I'd end up with, the hyperbolic functions again, because cosines of imaginary arguments end up being hyperbolics. So I need to find a way to just talk about the coefficient part, the just this part here, or I guess just this piece right here. So I guess the way to write this is I should write this as IR3 equals I times this, right? And IR4 equals this. And now R3 and R4 are defined correctly. Okay, good. So now we've got it right. All right, so that takes care of the spatial part. Now we remember, what about the other part, right? Well, the other part we've already solved. I'll do it in magenta. We already solved in the last lesson on damping, and we ended up with e to the minus kt times E of n, which we remember was ultimately the Fourier coefficients of everything, based on our initial conditions, times the cosine of, and I'm writing this down as 2 pi times the oscillation frequency t plus the damping constant k over 2 pi times these oscillation frequencies are hatted because they're inharmonic, right? And this is times the sine of 2 pi fn hat of t, right? So this was the solution, and we also learned that the inharmonic frequencies were given by the square root of lambda squared, lambda n squared, minus k squared over 2 pi. And this meant that the angular frequency, right, the angular frequency is given by lambda, given by lambda n squared minus k squared. Now, in the previous version, what we actually did is we ended up with a c squared right here, right? There was a c squared right there because we kept the c squared in the time piece of the expression. But when you move it to the space piece, it is now gone. So we just end up with these expressions. So the frequencies are still dependent on these numbers lambda, which we haven't solved for, but nothing else about that process changes. So we still know the time part of our solution. And so now we've got the structure of the whole answer, right? It's going to be this times this, right? We're going to multiply this expression here multiplied by that expression there, and then we do the Fourier analysis on En, which turns out it's going to be exactly the same as before. And that's the whole solution. And it looks like, well, this should be the same solution. But now we got to kind of solve for these constants. We still have these 4 constants. So let's get rid of those. All right, getting rid of the constant is the big deal here. So let's set this up. So this part here is the time part, right? This big part here, I'm putting it in brackets. And this part here is the space part. And now we're multiplying the time part and the space part together, right? So now this whole thing multiplied together equals x of x times t of t, which is u of x and t. So now we use our initial conditions. U of 0 for all time equals 0, and u at the scale length for all time equals 0. So the fact that, using just the first one, right, u of 0 of t, we plug in t for x. We plug in 0 for x everywhere, right? It doesn't matter what time is. And what do we get when we do that? Well, this guy, this hyperbolic sine and the regular sine go away. So b and c are gone, leaving us a hyperbolic cosine and d regular trigonometric cosine. So with x equals 0, this becomes just d hat, and with x equals 0, this becomes a hat. So this tells us that a hat plus d hat must equal 0, right? So that's what we learned from that. Now, I mentioned that the next boundary condition was the obvious fact that at the other end, at the bridge end, there's no displacement. But we're going to put that one on hold for a second because we need to introduce more boundary conditions because we are dealing with a fourth order equation. Look, we got 1, 2, 3, 4, and we have 5 variables left to find, right? So we have a lot of work to dig into here to figure all these things out. Plus there's lambda as well, right? The other boundary condition that exists now because we're dealing with moments and torques is that there is no moment. So if we look at our string, right, the string over here is held, there's these, basically, we're going to treat it like pins, right? There's pins there. There's a variety of boundary conditions that we could in principle apply. We could also say it's clamped, right? That wouldn't be too far off from being the way it really is. Except that clamped implies some things about the first derivative. We're just going to go with pinned. And what this basically means is at this point, there is no moments. There are no force moments at the two endpoints. So that tells us that uxx of 0 for all time equals 0. So we're going to deal with that right now. Now, the second derivative of this expression is actually, of course, very easy to solve for. We end up with two factors of the argument out front. So we're going to end up with, an example in this case, ar squared, ar1 squared cosine, hyperbolic cosine. And this will be b r1 squared hyperbolic sine. But again, this one goes away for the x equals 0. So we're only interested in these two. So we have a r squared plus d r squared equals 0. So we have to write a r1 squared, and this one we'll pick up a minus sign, minus d, that's a hat, minus d hat r3 squared equals 0. And then when we substitute in this, a plus d equals 0, right, we end up with a r1 squared minus r3 squared equals 0. Whoops, no, it's a plus sign, right? So the only way that can work is if a equals 0. And if a equals 0, by this, d must equal 0, or a hat and d hat. Phew. So the point of all that is that we can eliminate the hyperbolic cosine and the regular cosine from the answer. Okay, so that's what those two boundary conditions told us. Now, the boundary conditions at L are far more interesting. I mean, well, everything's interesting, but the boundary conditions at L are also very important. So let's look at those. First, let me rewrite these guys like this. So we have them all together. And now we're going to look at the other boundary conditions. So we're going to look at the moment and the displacement at the bridge. So in this case, the process is a little trickier, right? So we want to first write that we'll just break it down into just the x part. Remember, this is x of L here, and then this is t of t here. So we're saying that x of L, we know, equals b hat. So if I take these derivatives, well, first of all, if I just write down x of L, I need to replace these two x's here with L's, right? And capital L and capital L. And then if I take the second derivative, I get this expression. Oh, I feel like I'm missing a minus sign. Hold on. Yeah, of course, right? I mean, I'm missing a minus sign right here. Take two derivatives, you get a minus sign of a trigonometric function. So now, let's look at this. If I take this expression here and multiply it by, if I took this and multiplied it by r3 squared and then added these two expressions to each other, this would cancel with that, right? These two would cancel, and you would end up with, I guess you would end up with something that looks like x, second derivative of x at L minus R3 or plus R3 squared x at L, right? Which first of all has to equal 0 because that has to equal 0, that has to equal 0. And it would be B hat times B hat times R3 or R, wait, it would be B hat times the hyperbolic sine, B hat times the hyperbolic sine of R1L, right, times R3 squared plus R1 squared equals 0. Okay, so the only way that can be 0 is, well, first of all, it could be 0 if, so what this, the way to interpret this, let's see if I remember this right, the sine, the hyperbolic sine is 0 sometimes, but only when the argument is 0. R1 is not 0 and L is not 0, so this is not 0. These two are summed together, that's definitely not 0, so B has to be 0, which means the hyperbolic sine is out of our expression, right? It says B hat equals 0. Wow, so we did all that work to get down to the fact that the shape of the mode is still, just like in the damp case and just like in the ideal case, the shape of the mode is still just a straight up sine function, just like always, or just like the other two circumstances. So the stiffness does not end up changing the shape of the mode, at least under these circumstances. So that's interesting. So now we can get rid of this part of the expression and look even tighter at, now we can dig into En, right? And we still have to figure out what these frequencies are, right? We still have to figure out what these frequencies are because the reason we don't know the frequencies is we don't know lambda yet, right? We have to get into lambda, but that's going to be the next boundary condition. All right, so here we are, we're down to this part for x of x and this for t of t. So now we can apply the u of L for t must equal 0, which has to be c hat sine R3L must equal 0. Now, we could say that, okay, well, c hat 0 too, but then the whole solution collapses, right? So what we now need is, since sine is periodic, we now need R3L equals some multiple of pi to get sine to be 0. So that is very helpful. So R3L is some multiple of pi. So that is going to take a little bit of work, because remember, R3 was, where was it? R3 was, the way we defined it finally, was this expression right here, right? So let's take that expression and set it equal to n pi and see what we get. Not set it equal to n pi, but set it times L equal to n pi. So I guess I'll do that in black. That times L must equal n times pi. So you can kind of see what we got to do. The goal here is, well, what can we play with, right? Remember, everything's fixed. L is the scale length of the guitar. E is a material property based on the metal of the string. Mu is the geometry of the string and its density. So that's a material property of the string. Tension is set by the guitarist. So the only thing here is lambda. So this whole expression is a way of determining what lambda is, right? It's a way of determining what lambda is. So, so how are we going to nail that down? Well, I'll just sort of work through it here. I've got some notes, so I should get it right pretty quickly. But we're looking for R3 L equals n pi. So the first thing we're going to do is square both sides, because R3 is buried in this square root. So let's just square both sides, and that's definitely going to help us. So this gives us R3 squared equals n pi over L squared. So what is R3 squared? Well, R3 squared, if I got this right, is this thing with this square root erased, right? So that guy equals n pi over L squared, right? So now I'm going to take a t over 2ei out of the whole thing, right? So I can do that from the square root, right? Let's see. Let me make sure I'm getting this correct. T over 2ei, and what's left behind is going to be a square root of something, and it's going to be, well, the first part will be 1. The denominator, of course, this denominator is taken care of, and then that becomes 4ei lambda squared mu divided by t squared, right? And then minus 1. So this is where it's nice to have that little edge on your square root, right? And that has to equal n pi over L squared. And then I'm going to try to introduce a c squared here to simplify some things out. So remember that c squared equals t over mu. So if I put a c squared in, so c squared is just so if I got rid of the t squared and the mu, right, I would have the c squared would replace it, but it would have an extra mu in the numerator. Oh, no, it wouldn't. It would just leave a t behind in the denominator, right? It would leave a t behind. So it's nicer to have c. C is just a more the speed of sound for the wire. These two numbers almost always come together. Well, they don't. Obviously, they're not. I mean, there's a t sitting out there by itself. So, but the final expression, we like to have that c squared in there instead of the mu. But what I'm really after is I want to put this in terms of the harmonic frequency, right? So the harmonic frequency, F, is, let's see, it's C over 2L. C over 2L. So now if I put a L squared up here, right, then I'd have a C squared, L squared, and I have a 4, right? So this 4 is a built-in 2 squared. So this 4 over c squared L squared would be F. But I put an L squared up there, so I have to put an L squared down here. So then I end up with t over 2ei times the square root of 1 plus. And now I'm going to connect, take this, and this, and call that 1 over F, where F is the fundamental frequency. I'll call it F1 for the first harmonic, right? So then that gives me ei lambda squared over F1 squared, because remember it's c squared L squared over 4, and F1 is c over 2L, T, the tension, times the scale length squared minus 1, right? And that, so I'm trying to put these things in terms of things that are a little more intuitive, you know, things that we know about. We know the fundamental frequency, for example. We know this very well. But we're still, remember, we're after lambda. So this is just sort of house cleaning right now. And in fact, the ultimate expression of house cleaning is I'm now going to define a new constant. I'm going to define a constant B. And that constant is going to be ei over TL squared. And actually, I'm going to put a pi squared in there for convenience later on, right? And therefore, if I do that, this is going to become, I'll erase all of that, and this will become B lambda squared over F1 squared pi squared. Oh, and it here, this becomes, we got the T there, right? This becomes 1 over 2 BL squared, right? So BL squared. This, we're going to give a name later. It's called the Inharmonicity Coefficient, right? And it's a standard number, so that's why I'm working so hard to get it into the expression here. Meaning it's a number that's referred to pretty routinely. And we'll talk about it in a moment, because we're still working on solving. Remember, this is still, regardless of all the work we've done, this is still an equation for lambda squared, right? And now I think anybody can do the algebra to solve for lambda squared. Oh, there's a pi squared here. Pi squared, right? Pi squared. Because of the B. The B has a pi squared in its definition, right? And that has to do with converting from angular frequency to regular frequency. Because this is given as a regular frequency in hertz, not an angular frequency in radians per second, right? So with this definition and this expression here, right, can now be easily solved for lambda squared. And the result, or it can be solved for lambda, right? Lambda is going to equal, actually it's lambda n, remember, because there's this n here, right? So it all, lambda is going to depend on the value of n you choose. So lambda n, in fact, I should just put an n right there. Let me erase this here. Go back to the black, put the n right in there so we can see it. So lambda n is, when this is all said and done, is going to be 2, no, sorry. That would be if I didn't do the 2 pi. So lambda n is going to be and this is the solution that you should get if you solve this correctly. Lambda n ends up being an angular frequency, right? 2 pi times a regular frequency. This is a pure number, right? This all works out to be unitless. And b squared is the inharmonicity constant, right? So this is what lambda n is, not lambda n squared, right? This is the finally, in the end, there's a square root involved, right? See, how's that going to work, right? We're going to end up, squaring this term to get these guys out, and the pi squares will cancel. You'll end up with an n squared, and then ultimately you'll have to take the square root of something in order to get this lambda out. But this is the algebraic solution to this mess. So now, with this, we are knocking on the door of our answer, because once we know lambda n, we can go back to, where's our expression? This is our full expression, right? This times this is our full expression for the answer we seek, which is u of x and t, right? That's what this is. So we know that f hat n, the frequencies have to be placed in here, but we know what those frequencies are because we solved it back, or I cited them back here. Where did I cite them? Here, right? This is the time part of our solution, and this is the frequency. And notice the frequency had this damping piece in it, but it's waiting for us to calculate lambda n, which we just did. So now we write the frequency is equal to the square root of, and we're going to put in here our version of lambda m squared, k squared, over 2 pi. And this number here, what we put right in there, is the square of this. So with this, I'll paste this down to remind us what it is, and we will go ahead and just put it right in. And it's 2 pi n, the harmonic frequency, right? Oops, undo. Harmonic frequency times the square root of n squared, inharmonicity constant squared, plus 1, right? Minus the damping constant squared, right? All over 2 pi. Oops, this, and it's that squared, right? Because remember, lambda squared. This is lambda, so I got to take all of that and square it. And this is our new expression for the frequencies of oscillation. And notice it goes here. This whole mess goes in here, goes in here, and goes in here. And that is our solution for t. And then when we set t equals to 0, if we set t equal to 0, what happens is this part goes away. This part becomes 1, and it leaves behind just En. And that's when we learn that En has to be the Fourier coefficients that give us our initial condition, exactly like before. And it's the same initial condition as before. So En is going to have the exact same form as our original solutions that we did prior to this. That was true for the damped and the undamped. So En will end up being 2 times the initial string displacement times the scale length times the sine of n pi times the position of the pick over the scale length divided by the position of the pick times the scale length minus the position of the pick, harmonic number squared, pi squared. So this guy substituted in here, this guy substituted in there, and then you take the resulting expression, right, this whole thing, and you multiply it by, we got rid of that, we got rid of that, and we got rid of that, and you multiply it by that, and that is the final answer for u, x, and t. The one thing we didn't discuss much, but this guy right here, this piece, this is what sort of tells you why your string sounds different when you pick it in different places, because this is the pick position, right? This is the position of where you're actually executing your pick stroke, or your pick attack, and this is the scale length. So this number is less than L, and it's some fraction of L. So if this is halfway, it's L over 2, this number, this sign is going to cut back the amplitude of the vibration. And if you pick directly over the node of a mode, that mode won't sound at all. And this is the piece that eliminates that. Something we might talk about later. But anyway, so this frequency, right? Well, let's see what we got. If the harmonicity constant B is 0, then this expression is 1, and this becomes 2 pi n f1 quantity squared, right? And that is exactly the answer we got for just the purely damped expression. And if this k is 0 and b is 0, right, then we end up with 2 pi n f1 for the frequencies, which is the harmonic frequencies. So that is, it's 2 pi n divided by 2 pi. So the 2 pi's will cancel, converting the angular frequency to a regular frequency. So indeed, the limits both work. If B, which is the inharmonicity, goes to 0, right? If this goes to 0, then this limits to the damped expression. And if that and that go to 0, it limits to the ideal expression. And there you have it, right? There you have the final solution for the whole thing. Maybe I should write down the whole final solution. And here it is, right? This is our final solution right here. It's the sum of all the modes. Every mode is suppressed just like before. And now the frequency has this much more complex term in it than before. Remember the previous term. So this is the final expression, kind of written out in full LaTeX glory. This expression in here, right, there's the frequency, everything inside the square root with that 2 pi. And the old version with just damping and no stiffness looked like this. And it's a nice little exercise to see that this is the same as this with B set to 0. When B is set to 0, you actually get the same thing, which is an important fact. And when K is set to 0, you end up with what you would have gotten for just the wave beam equation. And there she is. So these now, the things to take note of is if you look at this, if this piece here is the frequency, right? So this is the angular frequency, and this is the sort of the non-angular frequency, the what's the word, the regular frequency in hertz, right? And what you see here is that the inharmonicity is related to B, right? If B is significant, if B is large, then the inharmonicity is significant. And the higher the harmonic, the more significant is the factor, because you want this square root here to be 1, right? When B is 0, this thing is 1. So if B is not 0, then it gets bigger. This gets bigger and bigger based on the harmonic. So the 100th harmonic has a huge contribution to the inharmonicity. So it's the opposite for the frequency related to just the damping, because when it's just the damping, it gets weaker and weaker with higher frequencies, and here it gets stronger and stronger with higher frequencies. So that's of note. And so the shift is the least when you have the fundamental frequency involved. And for the damping, the shift is the greatest when you have the fundamental frequency involved. So comparing those will be something that we might do in a different video. Okay, well, thanks for paying attention to all this mess, and